Hi, my name is Connor Getz,
My name is Kristen Stinson.
and together we're going to be presenting Project D for Project 1 of heat transfer. So for Project D, we are modeling a computer chip or a phone chip for the iPhone 13 that measures 2 centimeters by 2.5 centimeters and is negligibly thin. And then it's going to be cooled by a 5 centimeter by 7.5 centimeter heatsink. And there were two materials that we're going to be studying. We're going to be studying both aluminum and stainless steel. And because some hooligan put this on crooked, it is off center. So we were not able to make use of symmetry to make our lives a little bit easier. So we ended up going with 4 nodes for our model, and each node gets its own equation because we were not able to use symmetry. Kristen will be going over the different equations that we ended up going with. Some of our givens that were given in the problem statement are H is equal to 150 watts per meter squared Kelvin. And the ambient temperature, which is going to be on all sides of the heat sink, is T is equal to 20 degrees C. And that's going to be convection transfer because it is air that is surrounding it. Now, if we go up to the deliverables, we're going to be going through steps 1 through 4 of the solution procedure. And then we're also going to be going over our tool that we use to solve those 40 equations, which ended up being Excel. And we're going to be showing how that works and how we set it up. And now I'll hand it off to Kristen to talk about the math.
Alrighty, so as you can see, we started with the 4-step process for the solutions we've been using the whole year. Started with drawing a schematic of the heat sink and the chip together. It is off center, but we made sure the nodes line up just to make things a little bit more simple. The givens are on the left-hand side. I did make a small mistake with the H in writing 15 instead of 150. The assumptions we made to solve this is that it is a 2D problem, as Connor stated above. It's in steady state. There's constant K across the heatsink and the chip, and delta X equals delta Y at 1 centimeter. So starting off with the analysis, I broke it up into the type of node we were dealing with. So we have equations for chip nodes explicitly. The derivation can be seen on the right-hand side. Started with just the first law of thermo and broke it down into the Q's, solved it from there. T7, T8, T12, T13 are all the same, and T17 and 18 are a little different. They're just divided by 2 on the Q double dash because it was only getting half of that 6-watt power. So next we move on to the exterior nodes. Most of the equations are pretty similar to the ones we've been dealing with. The only difference is that the temperature node is not on the boundary, it's inside the boundary. So I had to derive that equation, but it's pretty similar. All of the exterior nodes besides the corners are going to be similar, if not the same. There are 2 other derived equations, one for those half nodes on the bottom, including those corners, and ones for those top corner nodes, just to make sure they're the same as the normal equations. Moving on to our interior nodes, they are the exact same interior nodes equations we've been using for this whole entire time. The initial equation can be written above, and if you scroll down a little bit further, you can see all of the individual T equations. Those interior nodes are the ones highlighted in pink, and then the rest of the exterior nodes are in yellow, just to keep track of our 40 equations we're putting into our Excel. Next, we'll move on to our Excel to see all of the equations input and how we used them.
Yeah, so we broke these up into sheets. So we have a sheet for steel, a sheet for aluminum, and then we have separate sheets to output the layouts. We ended up kind of creating in Excel a model of this system so that we could visualize the heat gradients. But starting with the table itself, because we have 40 different equations and each equation only has about 4 to 5 variables, we ended up having a lot of zeros. So we tried to color code all of the non-zero values to help visualize how this was looking in the matrix and check for any mistakes, but also just to make it easier for you to read. So here we have a 40 by 40 matrix, which is going to have all of our nodal equations. And then the other side of the equal sign is going to be in this constants column right here. And then if you look off further to the right, this is where we have our givens. And you'll see, because this is the aluminum sheet, or because this is the steel sheet, sorry, it is 14.4. And then we have a list of variables here just to keep everything straight. Now, all of these are going to link to the corresponding layout page. So this is the layout page for steel. So you're going to see our chip nodes are highlighted in orange. These would both have half of the chip contacting it, but because this is Excel, we couldn't make it a half node, unfortunately. So for representation's sake, they are both orange still. And you can see the temperature gradients. So that, in a nutshell, is how our Excel works. And then here is the same for Lumina. And then I'll hand it back to Kristen to talk about how confident we are.
So in terms of their equations derived, we're pretty confident that we got them mostly correct. We had some difficulties with those chip nodes, just theory-wise, but we both double-checked ourselves and went back, found that our Excel was a little bit funky in the beginning, and derived those equations again. And we feel pretty confident that we got mostly correct equations for those. And any of the equations that are normal that we've been using, we feel very confident on. But overall, if you're looking at the temperature gradients, especially for steel, it seems pretty close. 6 watts is not a lot of heat. There is an increase in heat, but it's not significant. And there's not anything crazy going on. So we do feel pretty confident that we did get this pretty correct for the most part.
Well, thank you for your time. That is all we have. And we look forward to seeing you in class.